A short while ago, scientists made a discovery that changed everything we knew about planets. They found worlds that do not orbit any star. These are lonely planets, lost in the darkness of space, wandering alone for billions and billions of kilometers. Imagine a place where the sun never rises, where the sky is always black and frozen. These planets were kicked out of their systems or were born alone, never knowing the light of a parent star. And the strangest part is that there may be more wandering planets than stars in our entire galaxy. This makes us ask, what happens on a world where night lasts forever? Get ready to fall asleep while listening to this video. Subscribe to the channel, leave your like, and comment where in the world you are watching from. Get comfortable and relax. Let us begin. Imagine a world torn from its star, cast adrift in the cold void of space. This isn't science fiction. It's the dramatic fate of countless planets ejected from their homes. The story of how a planet gets expelled begins in the chaotic early days of a solar system. When a star is born, it's surrounded by a swirling disk of gas and dust. And within this disk, planets start to form. It's a violent and messy process, with countless bodies colliding, merging, and competing for space. The stability of the system is fragile, and even small disturbances can lead to big changes over time. One of the most common ways planets are kicked out is through gravitational interactions with larger planets, especially gas giants like Jupiter. These giants have immense gravity, and as they migrate or interact with other bodies, they can act like gravitational slingshots, flinging smaller planets out of the system. It's a bit like a game of cosmic pinball, where the balls are planets and the bumpers are the gravitational fields of massive worlds. Another scenario involves the close passage of another star. In dense star clusters, stars often pass near each other, and when one star swings by a planetary system, its gravity can disrupt the delicate balance. The planet's orbits become unstable, and some might be ejected into interstellar space. This is more likely in young systems where planets haven't settled into stable orbits yet. Then there are binary star systems, where two stars orbit each other. If one star dies, say in a supernova explosion, it can suddenly lose mass, altering the gravitational dynamics and potentially releasing planets from their orbits. Even without a supernova, the complex dance of two stars can make planetary orbits unstable over time. The process of ejection isn't instantaneous. It can take millions of years for a planet to fully escape the gravitational pull of its star. During this time, it might have a highly elliptical orbit that gradually takes it farther away. Understanding these mechanisms is crucial for astronomers because it helps them estimate how many rogue planets are out there and where they might be found. Recent studies suggest that there could be billions of these free-floating planets in our galaxy alone, outnumbering stars. This challenges our traditional views of planetary systems and opens up new questions about the prevalence of life in the universe. If planets can be ejected and still potentially harbour life in subsurface oceans, then the habitable zone isn't just around stars, but anywhere there's internal heat. So, the genesis of exile is a fundamental aspect of planetary science, revealing the dynamic and often violent nature of cosmic evolution. The formation of planetary systems is inherently chaotic, beginning with the collapse of a molecular cloud. As the cloud contracts, it forms a protostar at the centre, surrounded by a rotating disk of material. This disk is where planetesimals, small bodies ranging from dust grains to several kilometres in size, accrete through collisions and gravitational attraction. Over time, these planetesimals grow into protoplanets, and, eventually, full-sized planets emerge. However, this growth process is not smooth. It involves numerous impacts and gravitational encounters that can scatter bodies throughout the system. The presence of gas giants exacerbates this instability. Jupiter-like planets, with their strong gravitational fields, can migrate inward or outward due to interactions with the gas disk or other planets. This migration can resonantly couple with smaller planets, leading to orbital perturbations that increase eccentricity. Eventually, the smaller planet's orbit becomes so elongated that it crosses paths with other bodies or reaches escape velocity, ejecting it from the system. This mechanism is particularly effective in systems with multiple giant planets, where their mutual interactions can create a dynamical chaos that boots out smaller worlds. Beyond internal dynamics, external factors play a significant role. In stellar nurseries, where stars are born in close proximity, gravitational encounters between stars are common. A passing star can inject energy into a planetary system, disrupting orbits and causing ejections. The severity of this disruption depends on the distance and speed of the flyby. A slow, close pass can be especially destructive. Simulations indicate that in dense clusters, such events can eject a substantial fraction of planets within the first 100 million years. Binary star systems present another complex environment. Planets in binary systems may orbit one star, S-type orbits, or both stars, P-type orbits. But stability is not guaranteed. The gravitational pull from both stars can lead to Lidov-Kozai oscillations, where the inclination and eccentricity of a planet's orbit vary cyclically, potentially leading to ejection if the eccentricity becomes too high. Moreover, if one star in a binary system evolves into a red giant or undergoes a supernova, the mass loss can unbind planets, sending them into interstellar space. The timescales for ejection vary widely. In some cases, a planet might be ejected within a few million years of system formation. In others, it might take billions of years. During the ejection process, the planet may experience extreme environmental changes. As its orbit widens, it moves farther from its star, causing temperatures to plummet. Any atmosphere might freeze out, and surface liquids would solidify. However, if the planet has a thick atmosphere or internal heat sources, it might retain some warmth. The journey after ejection is lonely and dark. Without a star, the planet has no external light or heat, relying solely on residual internal energy from accretion and radioactive decay. This internal heat could maintain subsurface oceans, especially in larger planets or those with active geology. The detection of rogue planets is challenging due to their faintness, but techniques like gravitational microlensing have proven effective. In microlensing, the planet's gravity bends light from a background star, creating a temporary brightening that reveals its presence. Surveys such as those by the Kepler Space Telescope and ground-based observatories have identified numerous candidates, suggesting that rogue planets are abundant. Some estimates indicate that for every star in the galaxy, there could be several free-floating planets. This abundance implies that ejection is a common outcome of planetary system evolution. It also reshapes our understanding of habitability. While surface conditions on rogue planets are harsh, subsurface environments could be temperate, powered by geothermal energy, hydrothermal vents, similar to those on Earth's ocean floors, might support ecosystems based on chemosynthesis. If life exists on such worlds, it would be entirely independent of stellar energy, expanding the potential niches for life in the universe. Furthermore, the study of ejected planets provides insights into the history of our own solar system. The late heavy bombardment period, around 4 billion years ago, might have been triggered by planetary migration that ejected several bodies. the hypothetical planet 9, thought to orbit far beyond Neptune, could be a captured rogue planet, illustrating how ejection and capture might shape system architectures. In summary, the ejection of planets from their stellar systems is a natural consequence of gravitational dynamics during and after formation. It involves interactions with giant planets, passing stars, and binary companions, occurring over millions to billions of years. The prevalence of rogue planets suggests that our galaxy is teeming with these lonely worlds, each with its own history of exile. Understanding their origins not only helps us map the galactic population, but also redefines the boundaries of where life might exist. As we advance our observational capabilities, we may uncover more about these dark wanderers, shedding light on the violent processes that govern planetary systems across the cosmos. But not all wanderers are exiles. Some are born orphans, emerging directly from the dark, cold clouds of gas and dust that drift between the stars. This process mirrors star formation on a smaller scale, where tiny, dense regions within a vast molecular cloud collapse under their own gravity. Imagine a pocket of this cosmic nursery, perhaps triggered by a shockwave from a nearby supernova or simply through random density fluctuations, beginning to contract. As it pulls in more material, it spins and flattens into a disk. But unlike typical planetary systems, there is no central star to anchor it. The object that forms is isolated from birth, a solitary world that never knows the light or warmth of a sun. These entities are often referred to as sub-brown dwarfs or planetary mass brown dwarfs, blurring the lines between what we call a planet and what we call a failed star. Their masses are too low to ignite sustained hydrogen fusion in their cores, which is the defining characteristic of a star. Instead, they glow faintly with the residual heat from their formation, gradually cooling over billions of years into the profound cold of interstellar space. The formation mechanism is akin to star formation, but stunted. Where a star would accumulate enough mass to shine, these objects plateau at masses similar to Jupiter or a few times larger, never crossing the threshold into stellar status. They condense from small, unstable agglomerations within the cloud, each becoming a self-gravitating body without ever being part of a larger planetary system. This direct collapse can happen in the darkest, most empty regions of space, far from any stellar nursery, suggesting that planet-like bodies can form almost anywhere there is sufficient material. The discovery of such objects has forced astronomers to rethink the very definition of a planet. According to the current International Astronomical Union definition, a planet must orbit a star, which would technically exclude these free-floating bodies. However, based on their physical properties, being massive enough to be rounded by their own gravity but not enough to fuse hydrogen, they share many characteristics with planets. This has sparked debates on whether classification should hinge on origin or intrinsic properties. If we consider formation in a protoplanetary disk as key, then these orphans are not planets. But if we focus on mass and shape, they could be. This isn't just semantic. It influences how we search for and study these objects, and it reflects our evolving understanding of cosmic diversity. Observations using infrared telescopes have been crucial in detecting these dark, cold worlds. Since they emit little visible light, their faint thermal radiation in the infrared spectrum is the primary way to spot them. Surveys like the Wide Field Infrared Survey Explorer have identified numerous candidates wandering near our solar system, some with masses just a few times that of Jupiter. The James Webb Space Telescope, with its superior sensitivity, is expected to find many more, potentially revealing a vast population hitherto invisible. The existence of these primordial orphans implies that planetary formation is not confined to stellar disks, but is a more universal process. It means that the building blocks of worlds can assemble independently in the void, expanding the potential locales where life might arise. If a planet can form and sustain itself without a star, then the concept of a habitable zone extends far beyond the regions around stars to include the lonely depths of interstellar space. For such a world, internal heat becomes the sole source of energy. This heat comes from the initial gravitational energy released during formation and from the decay of radioactive elements within its core over time. This heat diffuses outward, but in larger objects, it can persist for billions of years. This internal warmth could maintain subsurface oceans beneath a thick crust of ice, similar to moons like Europa or Enceladus in our solar system. In these hidden seas, hydrothermal vents might provide the energy and chemicals necessary for life to emerge. Based on chemosynthesis rather than photosynthesis, the ecosystem would be entirely independent of sunlight, thriving in perpetual darkness. The atmosphere of such a world would be starkly different from Earth's. Without stellar radiation to drive weather cycles, the atmosphere might largely freeze out, collapsing onto the surface as ice. However, if the planet has a thick, hydrogen-rich atmosphere, it could act as an insulating blanket, trapping heat and preventing total solidification. The surface pressure and composition would depend on the planet's mass and temperature, with heavier gases like nitrogen or carbon dioxide condensing first, leaving a thin, residual atmosphere. The weather patterns, if any, would be minimal, driven by internal heat rather than solar input, possibly featuring slow, sluggish winds or cryovolcanic eruptions that spew water, ammonia, DOT, or methane. The psychological and physical environment on such a world is almost unimaginable. The sky would be black, punctuated only by the distant, unmoving stars and the faint glow of the Milky Way. There would be no day or night, no seasons, and no sunrise to mark the passage of time. Time itself would be measured by geological or internal processes, such as the slow cooling of the core or the occasional meteor impact. For any potential life, evolution would occur in a context of extreme isolation and resource limitation, possibly leading to unique adaptations not seen on Earth. The discovery of these orphan planets also has implications for the prevalence of life in the galaxy. If they are as common as some estimates suggest, possibly outnumbering stars, then the number of potential habitats for life increases dramatically. Each one could be a sealed, independent biosphere, carrying life across the galaxy like a cosmic arc. This ties into the theory of panspermia, where life is spread between worlds via meteoroids or other carriers. Orphan planets could be vectors, transporting microbes between star systems. However, the challenges of detecting life on such worlds are immense. Without a star to provide light for spectroscopy, analysing atmospheres for biosignatures is difficult. Instead, scientists might look for signs of geological activity, like cryovolcanism, or indirect evidence of subsurface oceans through gravitational measurements or magnetic field interactions. Future missions, though technologically daunting, could involve sending probes to nearby rogue planets, using advanced propulsion to reach them within a human lifetime. The motivation for such exploration would be profound. To search for alien life in an environment completely divorced from stellar influence, which would revolutionize our understanding of biology. Moreover, studying these objects helps us understand the lower end of the mass spectrum in star formation. They represent the missing link between giant planets and brown dwarfs, offering insights into how gravity assembles matter across different scales. Their formation channels might include not only direct collapse, but also the ejection of protoplanetary embryos from young systems before they could fully form, adding another layer of complexity. In summary, the existence of planets that never knew a star expands our cosmic perspective. It shows that world formation is a versatile process, not limited to circumstellar disks, and that habitable conditions might exist in the most remote and dark places. As we continue to explore the cosmos, these lonely wanderers remind us that the universe is full of surprises, challenging our definitions and inviting us to look beyond the light of stars. The study of these orphan worlds is still in its infancy, but with advancing technology, we are on the cusp of uncovering their secrets, potentially finding that life is not a rarity but a common feature in the cold, dark vastness. Their story is one of independent origin, of worlds born from darkness, destined to wander alone, yet possibly teeming with hidden vitality. This understanding not only enriches our knowledge of planetary science, but also fuels the imagination about what else might be lurking in the unseen corners of our galaxy. Now, to truly grasp the reality of these orphan worlds, we have to envision the profound and unending darkness that defines their existence. Picture yourself standing on the surface of a planet that has never known a star. The first thing you would notice is the absolute blackness above, a void so complete it feels tangible. There is no sun, no moon, no dawn, and no dusk. Just an eternal, star-studded night. Your eyes would never need to adjust from light to dark because the darkness is constant and all-encompassing. The concept of a day simply does not apply here. Time loses its familiar rhythm, measured not in hours but in geological epochs or the slow beat of a planet's internal heart. Without a central star to orbit, the planet drifts through the cold gulfs between solar systems, and its sky is a static canvas. The Milky Way would not be a faint band, but a blazing river of light, so bright it might cast faint, shimmering shadows on the ground. Every star in the galaxy would be visible simultaneously, undimmed by atmospheric pollution or artificial light, presenting a view of the cosmos that is both breathtaking and isolating. This perpetual night fundamentally reshapes every aspect of the environment. There are no seasons as we know them, no spring blooms or winter chills driven by axial tilt and orbital position. Instead, any climatic variations would be dictated solely by internal forces. The weather, if it exists at all, would be a sluggish affair, driven by residual heat escaping from the planet's core. Imagine weak winds stirring a thin atmosphere, or perhaps no wind at all, leaving the landscape in a state of frozen suspense. The temperature at the surface would be brutally cold, often hovering just a few degrees above absolute zero, making the coldest places on Earth seem temperate by comparison. Any atmosphere present would behave differently. Without stellar radiation to drive convection and storms, the air could become stratified and stagnant. Gases might condense and fall as snow, not of water, but of nitrogen, oxygen, or methane, creating layers of exotic ice over billions of years. The surface pressure could be minuscule, or if the planet is large enough to hold a thick hydrogen atmosphere, it might trap enough internal heat to create a more uniform, though still frigid, environment. In such a case, the sky might have a deep, murky glow, but never brighten to a blue day. Light on the surface would come from two primary sources, the distant stars and the auroras. The starlight would be a constant, faint silver, illuminating the terrain in a soft, ghostly luminescence. You could read a book by it, but everything would be rendered in shades of grey and blue. More dramatic would be the auroral displays. If the planet has a magnetic field, it could interact with charged particles from the interstellar medium, creating curtains of light that dance across the sky in silent, spectacular shows. These auroras might be the only source of colour, flashing greens, reds, and purples against the blackness, powered not by a star but by the galaxy itself. The psychological impact of this environment cannot be overstated for a human. The absence of a day-night cycle would disrupt circadian rhythms almost immediately, leading to disorientation and a loss of time perception. The endless night could induce feelings of profound loneliness or cosmic awe, depending on one's perspective. For any native life forms, evolution would have sculpted senses adapted to eternal darkness. Eyes might be enormous to capture every photon, or perhaps useless, with other senses like hearing, touch, or magnetoreception taking precedence. Life would not measure time in days and years, but in internal biological clocks or environmental cues like geothermal activity. The very definition of habitat changes here. Without sunlight, photosynthesis is impossible, so any ecosystem would rely on chemosynthesis, where organisms derive energy from chemical reactions, such as those at hydrothermal vents. These vents, on Earth, support entire communities in the deep ocean, and on a rogue planet, they could be oases of warmth and energy in the frozen crust. The oceans, if they exist, would be buried under miles of ice, sealed away from the surface cold. In these submerged seas, the pressure could keep water liquid, and geothermal heat from the planet's core could sustain environments for billions of years. The chemistry of life would evolve without the influence of ultraviolet light or solar radiation, potentially leading to novel biochemical pathways. Molecules might be more stable, or conversely, more reactive in the cold, dark conditions. The surface, however, would be a wasteland preserved in time, with no rain, no winds, and no temperature fluctuations. Erosion would virtually cease. Impact craters from ancient asteroid collisions would remain pristine, unweathered for eons. Mountain ranges formed by tectonic activity would stand sharp and unchanging, and volcanic features might remain exactly as they erupted, with lava flows frozen in mid-motion. This creates a geological record of immense value, a snapshot of the planet's early history that on Earth has been erased by billions of years of weather and life. But it also means the landscape is static and dead, with no rivers carving valleys or glaciers grinding down peaks. The silence would be as profound as the darkness, with little atmosphere to carry sound. The world would be eerily quiet. You might feel vibrations through the ground, a distant quake or a cryovolcanic eruption, but hear nothing. This acoustic emptiness adds to the sense of isolation, making every movement feel solitary and significant for potential future human explorers. The challenges would be immense. Habitats would need to be entirely self-sufficient, generating their own light, heat, and oxygen. Power would likely come from nuclear sources or geothermal taps, as solar panels are useless. The psychological support systems would need to combat the effects of sensory deprivation and confinement. Yet, the scientific rewards could be staggering. Studying such a world could reveal secrets about planetary formation, the limits of life, and the history of the galaxy itself. Each rogue planet is a time capsule, drifting through space, and its eternal night holds clues to questions we are only beginning to ask. The very existence of these dark worlds forces us to expand our imagination of what a planet can be. It is not just a rock orbiting a star. It can be a solitary wanderer, shrouded in night, yet potentially vibrant with hidden oceans and unique life forms. As we look up at the starry sky, we now know that for every pinprick of light, there may be countless dark companions, invisible to our telescopes, but real and waiting in the void. Their endless night is not an emptiness, but a different kind of fullness, a realm where the universe shows a face we are only starting to recognize. Understanding this helps us appreciate the diversity of cosmic environments and the resilience of physical laws that operate even in the absence of light. It reminds us that life, if it exists, is not tied to sunlit worlds but can flourish in the most unexpected places, redefining our place in the cosmos. The study of these planets is pushing the boundaries of astronomy and biology, urging us to develop new technologies and theories as we continue to explore. We may find that the eternal night is not a barrier, but a gateway to new discoveries, revealing the hidden half of planetary existence that has been lurking in the dark all along. This journey into the dark is just beginning, and each new finding illuminates the incredible variety of worlds that share our galaxy, each with its own story written in the language of shadow and cold. The silence and stillness of these realms are deceptive, for they hold the potential for immense dynamic processes beneath the surface, waiting for us to listen and learn. In the grand tapestry of the universe, the rogue planets add a darker thread, one that completes the picture and shows us that the cosmos is far more varied and mysterious than we ever dreamed. Their eternal night is a fundamental aspect of their nature, shaping everything from their climate to their potential for life. And in understanding them, we understand more about the possibilities that lie beyond the light of stars. This exploration is not just about finding new places, but about redefining what it means to be a world. And in doing so, we expand our own horizons, looking past the familiar into the vast, dark, and beautiful unknown. But in the face of this relentless cold, these wandering worlds are not entirely defenseless. They possess a hidden fire within, an internal heart that fights a constant battle against the absolute zero of space. This internal heat is the key to their survival, preventing them from becoming completely frozen, lifeless rocks. Without the warmth of a star, the thermal destiny of a rogue planet hinges almost entirely on two things: the heat generated deep inside it and the insulating properties of any atmosphere it might have. The first major source of this vital warmth is primordial heat, a leftover from the planet's violent birth, when the planet formed, whether in a protoplanetary disk or from direct collapse. Countless collisions and the immense pressure of accretion released a tremendous amount of gravitational energy, which was trapped inside as heat. This heat is essentially the planet's birthright, a residual warmth that slowly leaks out over billions of years. The second crucial source is radiogenic heat, produced by the decay of radioactive isotopes within the planet's core and mantle. Elements like uranium, thorium, and potassium are unstable and break down over time, releasing energy in the form of heat with each radioactive decay event. This process acts like a natural, long-lasting nuclear reactor, continuously pumping thermal energy into the planet's interior. The combination of these two heat sources creates a thermal gradient, driving heat from the hot core outward toward the frigid surface. This outward flow of heat is what sustains geological activity. Even in the profound cold of interstellar space, it can create hotspots where the planet's crust is thinner or where molten material rises from the mantle on a rogue planet. This might manifest as cryovolcanism, where instead of molten rock, volcanoes spew water, ammonia, methane, or other volatiles that remain liquid or slushy due to the internal heat and pressure. These cryovolcanoes could build bizarre landscapes of ice and rock, with plumes of material erupting into the near vacuum and freezing into strange, crystalline structures. The presence of such activity is a clear sign that the planet is still geologically alive, its internal engine fighting to keep the cold at bay. The rate at which a planet cools depends heavily on its size. A larger planet, with a greater volume to surface area ratio, loses heat much more slowly than a smaller one. A super-Earth or a sub-Neptune-sized rogue world could retain significant internal heat for many billions of years, while a smaller, Mars-sized body would cool and solidify relatively quickly. This is why size is a critical factor in assessing the potential habitability of these lonely worlds. The composition of the planet also plays a role. A rocky planet with a metallic core will have different heat production and retention compared to an icy or gaseous world. But internal heat is only part of the equation. The atmosphere acts as a crucial blanket. Without an atmosphere, the planet's internal heat would radiate directly into space, and the surface would quickly approach the temperature of the cosmic background. However, if the planet has a substantial atmosphere, it can trap that escaping heat, creating a greenhouse effect that moderates surface temperatures. The composition and thickness of this atmosphere are paramount. A thick atmosphere rich in hydrogen could be incredibly effective at insulation. Hydrogen is a powerful greenhouse gas, and a dense envelope of it could maintain surface temperatures surprisingly high, perhaps even above the freezing point of water in some cases, despite the absence of a star. This means that the surface of such a hydrogen-rich rogue planet might not be a solid block of ice, but could have lakes or oceans of liquid water or other solvents, kept warm by the trapped internal heat. On the other hand, a thin atmosphere or one made of gases that condense at low temperatures would offer little protection. Nitrogen, oxygen, and carbon dioxide would all freeze out and fall as snow on a sufficiently cold world, leaving behind only a tenuous wisp of gas. In this scenario, the surface would be brutally cold, and any residual heat would be confined to the subsurface. The interplay between internal heat and atmospheric insulation defines the surface conditions. For a rogue planet with strong internal heat and a thick atmosphere, weather patterns might even exist, driven by the temperature difference between the heat escaping from below and the cold from above. These would be slow, sluggish circulations, perhaps with winds moving vast layers of exotic ices or gases. On a world with little atmosphere, the surface would be dead and static, a frozen museum preserving geological features for eons. The search for these worlds often involves looking for the faint signature of their internal heat. Since they emit no reflected starlight, astronomers rely on detecting their thermal radiation in the infrared part of the spectrum. A rogue planet that is still warm from formation or radioactive decay will glow faintly in infrared light. Telescopes like the James Webb Space Telescope are designed to be exceptionally sensitive to these infrared signals, allowing scientists to spot these dark, cold objects by their own feeble warmth. By analysing this infrared emission, researchers can estimate the planet's temperature and, from that, infer its age, size, and potentially its geological activity. A younger, larger rogue planet will be brighter in infrared than an older, smaller one. The detection of specific molecules in a thin atmosphere through spectroscopy could also hint at ongoing internal processes, like outgassing from cryovolcanoes. Understanding these heat mechanisms is absolutely vital for evaluating the possibility of life. If a rogue planet has enough internal heat to maintain a subsurface ocean of liquid water, it becomes a prime candidate in the search for extraterrestrial life. We see this principle in action in our own solar system on moons like Europa and Enceladus, which are heated by tidal forces from their giant planets. A rogue planet lacks those tidal forces, but its own internal heat could serve the same purpose. A thick layer of surface ice, perhaps tens of kilometers deep, would act as a fantastic insulator, protecting a subsurface ocean from the cold of space above. At the bottom of this ocean, hydrothermal vents driven by the planet's internal heat could provide a steady supply of energy and chemicals. In such an environment, life could potentially arise and thrive, based on chemosynthesis rather than photosynthesis. These ecosystems would be completely independent of sunlight, existing in perpetual darkness, sustained by the planet's own geothermal heart. The chemistry of life in such a place would be fascinating, potentially using different metabolic pathways than those on Earth. The pressure at the bottom of a deep subsurface ocean would be immense, possibly creating conditions for exotic states of matter or novel biochemical reactions. For any life forms, their entire world would be the ocean and the rocky core below. With no concept of a sky or a sun, evolution would favour adaptations to constant darkness, high pressure, and a reliance on chemical energy sources. The timescales for such life to emerge are also intriguing. A rogue planet with a stable internal heat source could maintain a liquid ocean for billions of years, providing a long, stable environment for life to develop and evolve. This makes them incredibly interesting targets for astrobiology. The journey of a rogue planet through the galaxy could even allow it to seed life elsewhere. If an impact on its surface were to eject material containing hardy microbes into space, that material could travel between stars and potentially infect other planetary systems, a concept known as panspermia. In this way, these lonely worlds could be silent arcs, carrying life across the vast interstellar distances. The study of internal heat sources is not just about planetary science. It connects to fundamental physics and our understanding of how matter behaves under extreme conditions. The slow cooling of a planet is a lesson in thermodynamics, a demonstration of entropy playing out on a cosmic scale. As we discover more of these rogue planets, we will be able to compare their thermal states and build a better picture of their diversity. Some might be geologically active worlds with subsurface oceans, while others might be frozen, dormant spheres. This spectrum of possibilities shows that the definition of a habitable world is much broader than we once thought. It does not require a star. It only requires a source of energy and a medium for chemistry, like liquid water, the internal heart of a rogue planet. Whether fueled by primordial heat or radioactive decay, is that source of energy. It is the engine that drives geology, potentially supports chemistry, and might even power biology in the most isolated environments imaginable. This realization forces us to expand our search for life beyond the traditional habitable zones around stars. We must now consider the vast, dark spaces between stars, where countless rogue planets drift, each with its own internal fire fighting the eternal cold. Their struggle against absolute zero is not a quiet one. It shapes their very nature and offers a beacon of hope for life in the most unexpected places. As our technology improves, we will learn more about these internal processes, perhaps one day sending probes to study them up close. Until then, we can only marvel at the resilience of these worlds and the hidden warmth that keeps them from succumbing completely to the frozen dark. And it's precisely this internal heat that opens up one of the most exciting possibilities for these lone wanderers. Vast, global oceans of liquid water hidden deep beneath a frozen, icy shell. We already have examples of this right here in our own solar system. Moons like Jupiter's Europa and Saturn's Enceladus are frozen worlds on the surface, but beneath their icy crusts, they hide immense salty oceans, kept liquid not by the sun but by the gravitational tug-of-war with their giant parent planets. This constant flexing generates internal heat through tidal forces. Now, take that concept and apply it to a rogue planet. It doesn't have a giant planet to squeeze it. but it has its own innate warmth, the primordial heat from its formation and the steady decay of radioactive elements in its core. If a rogue planet is large enough and has a sufficiently active interior, that heat flowing outward can be enough to maintain a liquid water ocean, completely insulated from the absolute zero of space by a roof of ice that could be miles or even dozens of miles thick. This transforms a seemingly dead ice ball into a potential aquatic world, a sealed biosphere adrift in the galaxy. The pressure at the bottom of such an ocean would be immense, crushing, but that very pressure, combined with the heat from below, is what prevents the water from freezing solid. It creates a stable environment where liquid water can persist for billions of years, a timescale long enough for the slow, patient processes of chemistry and perhaps even biology to get to work. The floor of this ocean wouldn't be a flat, sandy plain like in Earth's oceans. It would be a dramatic landscape of underwater mountains and deep trenches, all built from the planet's rocky mantle. And just like on Earth's ocean floor, there would likely be hydrothermal vents, where superheated water, rich in minerals, spews out from cracks in the crust. These vents are oases of energy and chemical potential. On Earth, such vents support entire ecosystems that thrive in total darkness, completely independent of the sun. The base of their food chain is built by microbes that perform chemosynthesis, using chemicals like hydrogen sulfide or methane as their energy source instead of sunlight. In the eternal dark of a rogue planet's subsurface ocean, this is the only way life could exist. There would be no plants, no algae, no photosynthesis. The entire ecosystem would be built from the ground up on chemical energy. Imagine bizarre tube worms, blind shrimp, and strange microbial mats all clustered around these deep-sea geysers, their world illuminated only by the faint, eerie glow of geothermal light, if any at all. The chemistry of this water would be fascinatingly alien. Dissolved salts, minerals leached from the rocky core, and complex organic molecules could create a rich soup. The water itself might not be pure H2O. It could be mixed with ammonia or other antifreeze compounds that lower its freezing point, helping it stay liquid at lower temperatures. This is a common feature on icy moons in our solar system and would be just as likely on a rogue planet. The sheer scale of these oceans is hard to comprehend. We are not talking about a small lake buried underground. We are talking about a volume of water that could rival or even exceed all the oceans on Earth combined, wrapped in a single, continuous layer beneath the ice. This means the habitable real estate on a single rogue planet could be enormous. A whole world within a world. But how could we ever know if such an ocean exists? We cannot see it directly. Instead, astronomers and planetary scientists look for indirect clues. One of the biggest giveaways is cryovolcanism. If the internal heat is strong enough, it can cause plumes of water vapour and other volatiles to erupt through fractures in the ice crust, shooting out into space. We've seen this spectacularly on Enceladus, where the Cassini spacecraft flew through these plumes and analysed their composition, finding water, salts, and even organic molecules for a rogue planet. Detecting such a plume would be incredibly difficult, but not impossible. A future powerful telescope might catch the faint signature of water vapour in the tenuous exosphere of a rogue world. Another clue is the planet's surface geology. An active interior with a subsurface ocean would cause the ice crust to be geologically young and constantly renewing itself. Much like the ice on Europa, it would be relatively smooth, with few impact craters, because new ice from the ocean below would well up and erase old features. A world with a frozen, solid interior would be heavily cratered, its surface an ancient record of bombardment. The way the planet interacts with its own magnetic field, if it has one, dot, could also be a telltale sign. A global dot, salty. Liquid water ocean is a good conductor of electricity. As the planet rotates, this moving conductive ocean would generate a magnetic field through a dynamo effect, or it would distort an existing field generated by the core. Detecting a magnetic field around a rogue planet would be a huge hint that there's something conductive and likely liquid inside. The potential for life in these buried oceans is what makes rogue planets such compelling targets for astrobiologists. The environment is stable, protected from the harsh radiation and asteroid impacts that plague surface worlds. It's a sealed, dark, warm bottle, and the ingredients for life, water, energy, and a rich mix of chemicals are all present. Life here would evolve in utter isolation, completely unaware of the universe outside its icy ceiling. There would be no day or night, no seasons, no concept of a sky for any creatures there. Their entire universe is the ocean and the thermal vents that sustain them. Evolution would favour adaptations to constant darkness, high pressure, and a reliance on chemical senses rather than sight. They might develop bioluminescence to communicate or hunt in the perpetual night. The discovery of life in such a place would be monumental. It would prove that life is not a fluke of Earth-like conditions, but a robust and universal phenomenon that can arise wherever there is liquid water and a source of energy, even in the coldest, darkest corners of the galaxy. It would mean that life is probably everywhere, hidden beneath the ice of countless worlds. This also expands the traditional concept of the habitable zone. We used to think life could only exist in a narrow band around a star where temperatures are just right for liquid water on the surface. But if life can exist in subsurface oceans powered by internal heat, then the habitable zone becomes the entire galaxy, any planet, whether it orbits a star or drifts alone, can be habitable if it has the right internal conditions. This includes not just rogue planets, but also icy moons around gas giants and even free-floating objects that were never part of a system. The implications for the abundance of life in the universe are staggering. There could be billions of these ocean worlds in our galaxy alone, each a potential cradle for life. Some of these oceans might be young, just beginning their long journey, while others could be older than Earth itself, giving life an even longer head start. For future human exploration, these worlds present both an incredible opportunity and a daunting challenge. Drilling through miles of solid ice to reach the ocean below is a feat of engineering we can barely imagine with current technology, but the scientific payoff would be unlike anything else. Sending a probe that could melt its way through the ice and release a submarine into the dark waters could allow us to directly search for life. Until then, we rely on our telescopes and our ingenuity to find these hidden oceans from afar. The study of these buried ocean worlds is forcing us to rethink what it means for a planet to be alive. It is not just about surface conditions or proximity to a star. It is about the dynamic interplay between a warm heart and a frozen shield, creating a sanctuary for chemistry and perhaps biology in the most unexpected places. These rogue planets, once thought to be the most barren and lifeless of objects, may in fact be the most common abodes for life in the universe. They are dark, silent arcs sailing through the void, each carrying within it the potential for a whole hidden world, teeming with activity we are only beginning to dream of. As we continue to search the skies, we must remember that the greatest secrets are often buried deep beneath the surface, waiting in the dark for a chance to be discovered. But while the interior might be a warm, watery sanctuary, the surface of a rogue planet is a brutally different reality, where the profound and unending cold wages a war against the very air itself. The atmosphere on such a world faces an existential threat. not from solar winds or impacts, but from simple, relentless chill. Without a star to provide external warmth, the surface temperature plummets, often settling just a few tens of degrees above absolute zero. In these conditions, the gases that make up an atmosphere don't just get cold, they undergo a phase change, condensing from gas directly into solid ice and literally snowing out of the sky. This isn't water ice. This is a precipitation of frozen air, where nitrogen, oxygen, and carbon dioxide turn into crystalline solids and accumulate on the ground in vast, barren fields. The process is a fundamental consequence of physics. Every gas has a specific freezing point, a temperature below which it cannot remain vapor, for the common constituents of Earth-like atmospheres. These points are far warmer than the ambient temperature of a rogue planet, nitrogen, which constitutes about 78% of our air, freezes at around minus 210 degrees Celsius. Oxygen solidifies at approximately minus 218 degrees Celsius. Carbon dioxide turns into dry ice at a comparatively balmy minus 78 degrees Celsius. On a rogue planet, where surface temperatures can easily be minus 250 degrees Celsius or colder, these gases have no chance. They will inevitably condense, freeze, and fall from the atmosphere, layer by layer, over millions of years. This atmospheric collapse is not a sudden event, but a gradual, relentless draining. The planet's gravity plays a critical role in this drama. A world with strong gravity, like a super-Earth, might initially hold a thick atmosphere, but the cold will still cause the heavier gases to freeze out. The atmosphere would slowly thin as its components are sequestered on the surface as ice. For a smaller planet with weaker gravity, the situation is even more dire. Not only do gases condense, but the lightest elements, like hydrogen and helium, which might remain gaseous, can achieve escape velocity and bleed away into space because the planet's gravitational pull is too weak to hold them. This double whammy, condensation and escape, can strip a world down to a bare, airless rock or leave it with an atmosphere so tenuous it's practically a vacuum. The result is a surface environment that is stark and static, with most of the atmosphere frozen solid on the ground. There is no medium for weather as we know it. There are no winds, no storms, no precipitation cycles. The air pressure, if any remains, would be negligible. Any residual atmosphere would be stagnant, composed only of the most reluctant gases, those with the lowest freezing points, like neon or argon. But even these might eventually succumb if the temperature drops low enough. The landscape would be a silent, frozen museum, covered in blankets of nitrogen snow, oxygen ice, and carbon dioxide frost. This sheet of frozen air would not be smooth. It might be sculpted over eons by the minimal internal heat, perhaps through slow sublimation and redeposition, or by the faint warmth from radioactive decay causing localized melting and refreezing. But for the most part, it would be unchanging, preserving features for billions of years because there is no erosion. The concept of a hydrological cycle is replaced by a cryological cycle, where the water is these volatile ices. But it would be an incredibly sluggish process. If it occurs at all, the sky above would be crystal clear, blacker than the deepest night on Earth, with the stars shining undimmed by any atmospheric scattering. There would be no blue sky, no clouds, no auroras if the magnetic field is weak due to the frozen core. The silence would be absolute, as sound needs a medium to travel, and with little to no atmosphere, vibrations would not carry. You could feel a meteor impact through the ground, but you would hear nothing. This collapse phenomenon is not just theoretical. We see smaller scale versions in our own solar system. On Pluto, for instance, nitrogen and methane condense and form frost on the surface, and its atmosphere thickens and thins with its seasons, though it has the faint warmth of the distant sun. On a rogue planet, there are no seasons, so the collapse is permanent and total. The moon, Triton, orbiting Neptune, has geysers of nitrogen gas, but on a rogue planet, such activity would be driven solely by internal heat, and any erupted gases would likely freeze out again quickly. Scientists study this atmospheric collapse to understand the evolution and fate of these lonely worlds. By modelling the thermodynamics and chemistry, they can predict what kinds of atmospheres might persist. For example, a rogue planet with a thick hydrogen atmosphere might avoid total collapse because hydrogen has an extremely low freezing point and can act as an effective greenhouse gas, trapping internal heat and keeping the surface slightly warmer. But even hydrogen will eventually condense if the planet cools sufficiently. The study also helps in detection. When searching for rogue planets with telescopes, astronomers look for the faint infrared glow from their surfaces or atmospheres. A world with a collapsed atmosphere will have a different thermal signature than one with a substantial gas envelope. If the atmosphere is largely frozen, the surface temperature will be uniform and cold, and any heat from the interior will be trapped under the ice, making the planet harder to detect. Conversely, a planet with a residual atmosphere might show signs of atmospheric composition through spectroscopy, if we can ever get precise enough measurements. This understanding is crucial for assessing habitability. While the subsurface might be habitable, the surface is utterly inhospitable to life as we know it. Any organisms would be confined to the deep ocean or the rocky interior, completely cut off from the outside. The frozen atmosphere also means no protection from cosmic rays, though the ice layer might provide some shielding. For future exploration, a landing on such a world would be treacherous. The surface would be composed of ices that might be brittle or unstable, and with no atmosphere. Any base would need to be entirely sealed and self-sufficient. The lack of atmospheric pressure also means that liquids would boil away instantly. So any water exposed on the surface would vaporize and then freeze, adding to the ice deposits. The long-term fate of a rogue planet's atmosphere is complete sequestration, over billions of years. As the internal heat dwindles, the planet cools further, and even the most volatile gases freeze out. The world becomes a cryogenic vault, its atmosphere locked in a solid state on the surface. This process highlights the delicate balance that allows Earth to have a stable atmosphere. Our planet's distance from the Sun and its internal heat keep temperatures in a range where gases can remain volatile. For rogue planets, that balance is broken, and the universe's cold reclaims the air. This knowledge not only helps us understand these specific objects, but also informs our view of planetary evolution in general. It shows that atmospheres are dynamic and fragile, and their survival depends on a complex interplay of temperature, gravity, and composition. As we discover more rogue planets, we will see a spectrum of atmospheric states, from worlds with thick, insulating envelopes to those that are essentially bare ice balls. Each data point adds to our understanding of how common or rare Earth-like conditions might be. The collapse of an atmosphere is a silent, slow-motion disaster, but it's a natural part of the life cycle for many worlds. It reminds us of the extreme environments that exist and the resilience of planetary bodies to adapt, even if that adaptation means freezing solid. In the grand search for life and understanding, these worlds teach us about limits and possibilities, showing that even in the darkest, coldest places, there can be structure and history written in the ice and the absent air, yet, for all their isolation, Some of these dark wanderers may not be entirely alone. They could be carrying their own companions in the form of moons, creating miniature planetary systems drifting through the void. When a planet is violently ejected from its home system, it doesn't necessarily travel empty-handed. If it has moons, the gravitational bond can be strong enough for them to be ripped away together, a family cast into exile as a unit. Alternatively, during its long journey, a rogue planet's gravity could capture other free-floating objects, asteroids, dwarf planets, or even other orphaned moons, swinging them into stable orbits. This means a rogue planet could have a single large moon, or even a whole system of smaller satellites, all orbiting a central world that itself orbits nothing but the galactic centre. These moons become incredibly important, potentially transforming from mere rocks into worlds of great interest, heated by the relentless gravitational tug-of-war with their parent planet, a process known as tidal heating. These moons could be far more hospitable than the rogue planet itself, even in the absolute cold of interstellar space. This internal friction generated by the moon's flexing and stretching as it orbits can provide a powerful and sustained source of heat. This is the same process that keeps the interior of Jupiter's moon Io molten and creates the subsurface ocean on Europa. For a moon of a rogue planet, this tidal energy could be the only thing preventing it from becoming a completely frozen block. It could maintain a liquid water ocean beneath a thick, protective ice shell, creating a sealed, warm habitat entirely independent of starlight. The environment on such a moon would be surreal. Its sky would be dominated not by a sun, but by the immense, dark bulk of its host planet, a colossal sphere that might fill a significant portion of the heavens. This primary world would not shine with its own light, but it would reflect the faint, collective glow of the distant Milky Way, creating a soft dot, ghostly illumination on the moon's surface. The planet would go through phases, much like our moon, but these phases would be defined by the reflected light of the galaxy, waxing and waning in a slow, cosmic rhythm. The surface of the moon would be a frozen wasteland, but below, in the dark, pressurized ocean, life could find a way. Hydrothermal vents on the ocean floor, powered by the moon's internal heat, could spew mineral-rich water, providing the energy and chemicals needed to sustain ecosystems based on chemosynthesis. Entire food chains could evolve in these abyssal plains, with organisms that have never seen light, their world defined by heat, chemistry, and the constant, subtle pull of the giant world above. The presence of such a moon system also increases the chances of geological activity. Tidal forces can drive cryovolcanism, causing plumes of water and other volatiles to erupt from the moon's surface. If the moon has a thin atmosphere, these plumes could even create a transient, localized weather system, with gases freezing out and falling as snow. For astronomers, detecting these moons is a tremendous challenge, but not impossible. Indirect methods, like timing the microlensing events of the parent planet, could reveal the gravitational influence of unseen satellites. Future direct imaging telescopes might be able to resolve a particularly large moon from its parent world. The existence of these binary or multiple systems dramatically expands the potential for habitable niches in interstellar space. While a lone rogue planet might have a habitable subsurface ocean, a moon heated by tides could have a much more active and long-lived ocean, as tidal heating can persist for billions of years as long as the orbital dynamics remain stable. These moons are like archipelagos of warmth in a dark, cold ocean, each one a potential haven for life. They represent a second chance for biology in an environment that seems utterly inhospitable at first glance. The dynamics of such a system are fascinating. The orbits would be stable over astronomical timescales, as there are no other large bodies to perturb them. The Moon's orbit would be a simple, elegant ellipse around its planet, a dance of two bodies in an otherwise empty ballroom. The planet itself would experience tides from its moon, though these would be minimal unless the moon was very large. The entire system would travel through the galaxy as a coherent unit, a tiny, self-contained universe for any potential life on such a moon. Its universe would be incredibly small. The sky is a permanent black, with the parent planet as the most prominent and unchanging feature. The concept of a year, or any orbital period around a star, is meaningless. Time would be measured by the moon's orbit around the planet, and by the slow geological cycles of its interior. Evolution would proceed in utter isolation, with no exchange of material with other worlds, making the ecosystem truly unique. If intelligent life were to arise in such a place, its entire cosmology would be built around the parent planet. It might be seen as a god, a world, or a prison. The discovery of other stars would be a philosophical revolution, revealing that their dark system is not the entirety of existence. The potential for such moon systems also affects the theory of panspermia. If a moon has life, an impact could eject material containing microbes into space. While the moon's gravity might recapture some, other material could be flung into interstellar space, potentially seeding other systems. Alternatively, the debris could travel to another moon within the same system, spreading life between different oceanic environments. This means a single rogue planetary system could have multiple inhabited worlds, a miniature interstellar community for human exploration. A moon of a rogue planet might be a more appealing target than the planet itself. The energy required to land on and leave a moon is typically less than for a large planet. A base on such a moon could study the subsurface ocean directly and use the parent planet as a gravitational anchor for further operations. The psychological effect for explorers, however, would be intense. Living under a giant planet that never moves in the sky, in perpetual darkness, would be a profound test of human resilience. The study of these miniature systems helps us understand the limits of gravitational binding and orbital stability. It shows that the processes of planet and moon formation are robust, capable of creating complex systems that can survive the trauma of ejection. As we discover more rogue planets, we will inevitably find that some have companions, and each discovery will rewrite our understanding of how common such arrangements might be. They are a testament to the complexity of the cosmos, demonstrating that even in the most lonely of places, gravity can create bonds that foster worlds within worlds, and perhaps life within life. But if life were to take hold in these lightless oceans, it would have to build its world on a completely different foundation, one that never sees the sun. Here on Earth, practically every ecosystem is ultimately powered by sunlight, with plants and algae using photosynthesis to convert solar energy into chemical energy. But in the perpetual dark of a rogue planet or its moon, that entire model is useless. Any biosphere there would have to be built from the ground up on chemosynthesis, a process where organisms derive energy not from light, but from chemical reactions. This is not some far-fetched idea. We have living proof right here on Earth, at the bottom of our oceans, around hydrothermal vents. There are thriving communities that exist in total darkness. The base of their food chain is made up of microbes called chemoautotrophs. These incredible organisms can take inorganic chemicals, like hydrogen sulfide or methane that spew out from the Earth's crust, and use them to produce organic molecules and energy. They do this through a series of chemical reactions, essentially eating rocks and gases to survive. This process is the only way life could get started and persist on a world without a star. For a rogue planet, the energy source wouldn't be a distant fusion reactor, but the planet's own internal heat. This geothermal energy drives the geology that releases these key chemicals into the environment, whether it's a subsurface ocean or a deep aquifer. The prerequisites for such a dark biosphere are relatively straightforward, though each is crucial. First, you need a liquid medium, and water is the best candidate we know. Its properties as a solvent are unmatched for facilitating the complex chemistry of life. Second, you need a source of energy. On a rogue planet, this could be the heat from radioactive decay in the core, or from the planet's primordial formation, which drives hydrothermal systems. Third, you need a rich supply of chemical nutrients, elements like carbon, hydrogen, dot, nitrogen, oxygen, phosphorus, and sulfur, and also various metals. These would be leached from the rocky mantle by hot water circulating through the crust, just like at Earth's deep sea vents. If these three things are present, liquid water, period, chemical energy, and nutrient diversity, then the stage is set for chemistry to potentially transition into biology. The ecosystems that could develop would be utterly alien to our experience. There would be no plants, no algae, no green anything. The primary producers, the equivalent of our plants, would be these chemosynthetic microbes. They would form mats on the seafloor or float in the water, harnessing the energy from chemical disequilibrium. Around hydrothermal vents, these microbes could support a whole web of life. We might find filter-feeding organisms akin to clams or tube worms, grazing on the microbial mats. Predators could evolve, hunting the grazers. But all of this would happen in total darkness, so vision would likely be non-existent or secondary. Life forms might rely on other senses, vibration detection, chemical sensing, or even sensitivity to electrical or magnetic fields. The pressures in these deep oceans would be immense, so organisms would need to be adapted to withstand crushing forces, perhaps with flexible bodies or strong internal structures. The temperature around vents could be scalding hot, while just a short distance away, the water would be near freezing, creating sharp gradients that life would have to navigate. The chemistry of life itself might be different. While we expect water to be the solvent, the specific molecules used for metabolism and structure could vary. On Earth, life is based on carbon, and it likely would be elsewhere due to carbon's versatility. But the pathways could be novel. Enzymes might operate optimally at different temperatures or pressures. The genetic material might not be DNA as we know it. It could be a similar molecule adapted to stability in those conditions. The timescales for evolution in such a closed system are fascinating. With no connection to the outside, evolution would proceed in isolation, potentially leading to unique and bizarre forms not seen anywhere else. The concept of species would be confined to that single ocean, with no gene flow from other environments. This makes each rogue planet's ocean a unique experiment in biology. If life arises, the discovery of life in such a place would be one of the most profound in human history. It would prove that life is not a fragile phenomenon dependent on the specific conditions of a sunlit planet, but a robust and fundamental process of the universe. It would mean that life can start and thrive in the most isolated and seemingly hostile environments, as long as the basic ingredients are there. This greatly expands the number of potential habitats in our galaxy. Suddenly, every rogue planet with a warm, wet interior becomes a candidate for life, and since there might be billions of these worlds, the probability of life being common in the universe skyrockets. For astrobiologists, the search for signs of this dark life is challenging. We cannot see it directly. Instead, we look for biosignatures, chemical imbalances in the atmosphere or on the surface that could only be explained by biological activity, for a rogue planet with a subsurface ocean. Detecting such signatures is incredibly difficult because the biosphere is hidden under miles of ice. However, if there is cryovolcanic activity, where plumes of water from the ocean are ejected into space, a spacecraft could fly through those plumes and analyze their composition, just as we did with Enceladus. Finding complex organic molecules or specific ratios of gases in such a plume could be a strong hint of life. Another approach is to look for heat signatures or geological activity that suggests a dynamic interior, which is a prerequisite for sustaining such ecosystems. The implications for humanity's future are also significant. If these dark biospheres are common, then as we venture out into the galaxy, we might find that life is the rule, not the exception. It also means that we must be careful about contamination. Our probes could inadvertently introduce Earth microbes into these pristine environments, or bring back alien organisms that could have unknown effects. The study of these systems also pushes the boundaries of our understanding of chemistry and biology. How does life begin without the energy input from the sun? What are the minimum requirements for a self-sustaining biosphere? Experiments on Earth that simulate these dark, high-pressure environments can help us answer these questions. In the end, the possibility of life in the dark teaches us humility and expands our imagination. Our Earth-centric view of life is just one possibility in a vast cosmos. The universe is likely filled with dark, cold worlds that are, against all odds, teeming with life, each a silent testament to the power of chemistry and the persistence of biological processes. As we continue to explore, we must keep our minds open to the strange and wonderful forms that life might take. Far from the light of any star, finding these dark, isolated worlds is one of the greatest technical challenges in modern astronomy. How do you see an object that emits almost no light and drifts against a backdrop of perfect blackness? You cannot use traditional methods that rely on observing the dimming of a star as a planet transits in front of it, because these planets orbit no star. The primary tool for this cosmic hunt is a phenomenon predicted by Einstein's theory of general relativity called gravitational microlensing. Here is how it works. Imagine a rogue planet drifting through space, and far behind it, a distant background star dot, the planet's gravity, while weak, acts like a tiny lens, bending and distorting the fabric of space-time around it. As the planet moves, it briefly passes in front of the background star from our viewpoint on Earth, for a short period, which could be anywhere from a few hours to a couple of days. The planet's gravitational field focuses the light from that distant star, making it appear temporarily brighter. It is a very subtle effect, but sophisticated telescopes can detect this characteristic brightening and dimming. The shape and duration of this light curve tell astronomers the mass of the object causing the lensing, allowing them to distinguish a Jupiter-sized world from a smaller, Earth-sized one, and even hint at its distance. This method does not require the planet to emit any light of its own. It solely relies on its gravity. The downside is that each event is a one-time occurrence. The alignment will never happen again, so it is a fleeting glimpse. Large-scale surveys like the Optical Gravitational Lensing Experiment and the upcoming Nancy Grace Roman Space Telescope are designed to continuously monitor hundreds of millions of stars to catch these rare and precious events. Another promising technique is direct detection in the infrared part of the spectrum. Even though rogue planets are cold, they are not at absolute zero. They glow faintly with the residual heat from their formation and radioactive decay. This warmth is emitted as infrared light. Telescopes with extremely sensitive infrared detectors, like the James Webb Space Telescope, can potentially spot these faint thermal signatures against the cold background of space. This is especially feasible for younger, warmer rogue planets that are relatively close to our solar system. The challenge is distinguishing them from distant galaxies or brown dwarfs, and it requires long exposure times and advanced image processing to tease the signal from the noise. A third method involves looking for occultations. If a rogue planet passes directly in front of a distant star, it could cause a very brief, tiny dip in the star's light, not from gravitational lensing, but from simply blocking it. This is incredibly difficult to detect because the planets are small and the alignment must be perfect. But with precise and frequent monitoring of the sky, it might be possible to catch these shadows. Each of these techniques provides a different piece of the puzzle. Microlensing gives us mass and a rough distance. Direct infrared detection can give us temperature and, through spectroscopy, potentially the composition of any thin atmosphere. Occultations could provide size estimates. By combining data from all these methods, astronomers can build a statistical picture of the rogue planet population. They can estimate how common they are, their typical masses, and their distribution throughout the galaxy. The hunt is like listening for a whisper in a hurricane. It requires patience, immense computational power, and a bit of luck, but every confirmed detection is a major victory, revealing another piece of the dark, unseen structure of our Milky Way. These worlds are ghosts, but by using the fundamental laws of physics as our tool, we are slowly learning to see in the dark. The technology for this search is constantly improving. New algorithms are being developed to sift through the immense datasets from sky surveys more efficiently. Future telescopes, both on the ground and in space, will have larger mirrors and more sensitive instruments, pushing the boundaries of what we can detect. The goal is to move from finding a handful of these objects to mapping their population in detail, understanding whether they are more common in certain regions, like the galactic bulge or the spiral arms. This cartography of the void will tell us not just about the planets themselves, but about the history of our galaxy. The number and types of rogue planets we find will constrain models of planetary system formation and dynamics. If we find a vast number of Earth-mass rogue planets, it would suggest that the process of ejection is very efficient and that many rocky worlds are cast adrift. This has profound implications for the potential of life, as these could be the dark ocean worlds we discussed. The search is also a testament to human curiosity and ingenuity. We are developing ways to find the seemingly unfindable, to chart the invisible geography of the space between the stars. It is a reminder that exploration is not just about going to places. It is about developing new ways to see. The darkness between stars is not empty. It is a new frontier, and we are just beginning to learn how to explore it. Every flicker of a distant star, every faint point of infrared light, could be a new world, waiting in the silence to be discovered. This meticulous work, conducted by teams of astronomers around the world, is slowly pulling back the curtain on a hidden component of our cosmic neighbourhood, proving that the galaxy is far more rich and dynamic than we ever imagined, filled with countless lonely travellers on endless journeys through the night. But as our methods for detecting these ghostly worlds have improved, the data has revealed a reality that is both staggering and humbling. Rogue planets are not rare anomalies, but likely the most common type of planet in our galaxy. Statistical analyses from gravitational microlensing surveys are painting a picture of an invisible population so vast that it fundamentally reshapes our understanding of cosmic demographics. The numbers emerging from these studies are almost incomprehensible. Current estimates suggest there could be billions, or even trillions, of these free-floating worlds within the Milky Way alone. Some models indicate that for every star in our galaxy, there might be several rogue planets, meaning they could easily outnumber the stars themselves. This is a profound shift in perspective. For centuries, we assumed planets were, by definition, satellites of stars. But now we are faced with the possibility that the dominant form of planetary mass in the galaxy is untethered, drifting in the dark between stellar systems. This abundance challenges the very core of traditional planetary formation models. These models, largely based on our own solar system's orderly structure, did not predict that the process of planet building would be so violent and chaotic that it would eject such an enormous number of worlds. It seems that the early lives of planetary systems are far more dynamic and unstable than we thought, with gravitational interactions routinely flinging planets out into the void. The implication is that ejection is not a rare catastrophe but a common outcome, a standard part of planetary system evolution. This means that our own solar system, with its stable orbits over billions of years, might be the exception rather than the rule. The galaxy could be filled with a vast, unseen swarm of dark worlds, a kind of planetary dark matter that we have only just begun to account for. Just as dark matter makes up most of the mass in the universe but does not interact with light, this population of rogue planets represents a massive amount of ordinary matter that has been effectively invisible to us until now. Confirming the true scale of this population would revolutionize our understanding of the architecture of planetary systems and the distribution of mass throughout the galaxy. It would force us to rewrite the textbooks on how planets form and evolve. The gravitational influence of these countless unseen bodies could even play a role in the large-scale dynamics of the galaxy. Though their individual masses are small, their collective mass might be significant. Furthermore, if life is indeed possible on these worlds, as we've explored with subsurface oceans and internal heat, then their ubiquity has breathtaking implications for the prevalence of life in the universe. If there are more rogue planets than stars, and even a small fraction of them are habitable, then the number of potential abodes for life skyrockets. Life would not be confined to the thin, warm zones around stars, but could be flourishing in the cold, dark vastness everywhere. This means life could be incredibly common, though almost entirely hidden from our current view. Buried under ice or deep within rocky crusts, the search for extraterrestrial life would need to expand its scope dramatically, considering these dark, isolated ecosystems as prime targets. The idea of life being a cosmic commonplace gains immense weight from this discovery. It suggests that the ingredients and conditions for life are so robust that they can arise and persist in the most isolated and energy-poor environments imaginable. This also ties into the theory of panspermia. With so many rogue planets acting as potential arcs, life could be spread between star systems by these drifting worlds, seeding the galaxy with biological material. The technological and philosophical implications are equally profound. For future exploration, it means that the galaxy is far more populated with worlds than we ever dreamed. Though most are dark and silent, it redefines our place in the cosmos. We are not inhabitants of a special, star-lit world in a universe of similar worlds, but rather, we live in one variant of a planet, the illuminated kind, in a cosmos dominated by dark, lonely wanderers. This new perspective is both exhilarating and sobering. It expands the canvas of potential life and complexity, but it also highlights our own isolation in a sea of darkness. The continued study of this invisible population is crucial. Upcoming missions like the Nancy Grace Roman Space Telescope are expected to detect thousands more of these objects through microlensing, providing the data needed to refine our estimates and understand their distribution. Are they concentrated in the galactic bulge, where stellar densities are high and gravitational interactions are more frequent, or are they evenly spread throughout the spiral arms? Each discovery will help us piece together the history of planetary ejection and the dynamic processes that shape our galaxy. The challenge remains immense, as these planets are faint and difficult to characterize. But with advancing technology, we are on the cusp of mapping this hidden archipelago. In the end, the realization that rogue planets may be the silent majority forces a cosmic humility upon us. It shows that our understanding of the universe is always incomplete, and that the most common things can be the hardest to see. The darkness between stars is not empty. It is teeming with worlds, each with its own history and potential. As we look up at the night sky, we must now imagine not just the points of light, but the countless dark companions drifting among them. A vast, invisible population that makes the galaxy a much more crowded and interesting place than we ever knew. This knowledge transforms our vision of the cosmos from a collection of stellar systems to a dynamic fluid of wandering worlds. And in doing so, it opens up new frontiers for science, imagination, and the eternal quest to understand our place in the universe. The journey to comprehend these ghosts is just beginning, and each new piece of data brings us closer to seeing the full, rich tapestry of our galactic home. Once ejected from its stellar home, a rogue planet does not simply hang motionless in space. It becomes a navigator on an epic, solitary journey across the galaxy, following its own silent orbit around the galactic center. This voyage is fundamentally different from that of a star with a planetary system. A star's path is smoothed and stabilized by the collective gravity of its entourage, a kind of cosmic inertia. A rogue planet, in contrast, is a singular body, a lone traveller subject to every subtle gravitational pull and push from the immense structures it passes. Its speed can be tremendous, often reaching hundreds of kilometers per second, a velocity imparted by the violent gravitational slingshot that expelled it. This journey is measured not in years but in billions of years, a timescale that dwarfs human history. The planet will cross vast and varied territories within the Milky Way. It may drift through the relatively empty voids between the spiral arms, where the interstellar medium is thin and cold. Later, it might plunge into one of the galaxy's bustling spiral arms, where star density is higher, and the risks of close encounters increase. It could even pass through dense molecular clouds, vast nurseries of gas and dust where new stars are being born. Though the planet itself is an ancient relic from a system long gone, throughout this pilgrimage, the planet is exposed to the harsh environment of interstellar space, cosmic rays, high-energy particles accelerated by distant supernovae and black holes, constantly bombard its surface or whatever thin atmosphere remains. Without a protective magnetic field or a thick atmospheric shield, this radiation would sterilize the surface, but it would be largely irrelevant to any life safely nestled in a subsurface ocean, protected by kilometers of ice and rock. The planet's trajectory is not a simple, elegant ellipse like the planets in our solar system. It is a path constantly perturbed by distant gravitational influences, the collective pull from passing star clusters, the tidal forces from the galactic disk, and the gentle yet persistent tug from dark matter all work together to sculpt its course over eons. This makes predicting the long-term path of any specific rogue planet nearly impossible, as it is a chaotic system sensitive to tiny changes in initial conditions. For most of its existence, the journey is one of profound isolation. The distances between stars are so vast that close approaches are exceedingly rare. The planet will spend millions of years without coming anywhere near another stellar system, a dark ship sailing an endless, black ocean. However, on rare occasions, its path may lead it close to another star. This stellar flyby is a moment of both peril and opportunity. The star's gravity can perturb the planet's orbit, altering its course through the galaxy. If the encounter is very close, the star's gravity could potentially capture the planet, ending its nomadic existence and binding it to a new stellar parent. This is one hypothesized origin for the potential Planet 9 in our own outer solar system, a rogue planet captured by the sun's gravity in the distant past. Alternatively, the close pass could disrupt the Oort cloud of the star system, sending a shower of comets inward, potentially causing a bombardment on any inner planets. The rogue planet itself could also feel the effects. Its own system of moons, if it has any, destabilized by the stellar encounter. The study of these trajectories is more than just tracking motion. It is a form of cosmic archaeology. By simulating the paths of rogue planets backwards in time, astronomers can attempt to trace them to their origin points, understanding which regions of the galaxy are most efficient at ejecting worlds. This can reveal the dynamic history of the galaxy itself, showing periods of intense stellar interaction in dense clusters that might have launched countless worlds into the dark. These planets are silent witnesses to the galaxy's history, carrying with them the kinematic fingerprints of their violent birth. For a planet with a subsurface biosphere, this journey is its entire universe. The life within its hidden ocean would be completely unaware of the grand voyage it is on. They would not know of the spiral arms they traverse or the distant stars they pass. Their world is the ocean, the rocky core, and the ice ceiling above. The concept of a journey is meaningless to them. Their reality is static and confined, even as their world moves at incredible speeds through the galaxy. This presents a fascinating duality, a world that is, internally, a stable, isolated capsule and, externally, a dynamic traveller on a billion-year pilgrimage. The resources available to such a world are finite, unlike a planet in a stellar system, which can receive a constant, if faint, trickle of material from cometary impacts. A rogue planet is truly alone. Its initial endowment of water, minerals, and radioactive elements is all it will ever have. This makes the longevity of its internal heat and the sustainability of its ocean entirely dependent on its initial mass and composition. A larger planet can last longer, its geological engine persisting for billions of years, while a smaller one may cool and freeze solid, its internal sea turning to ice. The ultimate fate of these cosmic navigators is uncertain. Some may eventually be captured by a star, as mentioned. Others might, in a universe governed by probability, collide with another object. Though the chances are infinitesimally small, most will likely continue their journeys until the galaxy itself evolves, perhaps being ejected from the Milky Way during a future collision with the Andromeda Galaxy, or continuing to orbit the galactic core until the stars themselves burn out. They are the ultimate long-distance travellers, their voyages so immense that they make human history seem like a single blink in time. Understanding their navigation is key to appreciating the full scope of planetary existence. It shows that planets are not static fixtures but dynamic entities with life stories that include birth, exile, epic journeys, and potentially a final resting place. This perspective enriches our view of the cosmos, revealing it as a fluid, ever-changing environment where worlds are in constant motion, and our own solar system is just a temporary, stable haven in a galaxy filled with restless wanderers. Their silent, endless journey is a testament to the scale and dynamism of the universe, a reminder that what we see as the fixed stars are just the backdrop for a much larger, darker, and more mobile population of worlds. The sheer scale and loneliness of these rogue planet journeys naturally leads to a chilling thought experiment. What if it happened to us? Imagine the Earth itself was suddenly torn from the Sun's gravitational embrace and cast into the interstellar void. The change would be immediate and catastrophic. First, the light would vanish. The Sun would simply wink out, plunging the entire planet into profound darkness within minutes. The moon and stars would remain, providing a faint, ghostly illumination. But the primary source of light and energy for our world would be gone forever. The temperature would begin to plummet rapidly. Within a week, global average surface temperatures would fall below freezing. Within a year, they would approach negative 100 degrees Celsius, and in a matter of centuries, the planet would stabilise at a bone-chilling negative 240 degrees Celsius. Just a few tens of degrees above absolute zero, the sky would not be blue but black, a perfect void punctuated by the unmoving, brilliant stars. The psychological impact on humanity would be unimaginable. The sudden, permanent night would induce widespread despair and disorientation. Our circadian rhythms, tuned to the 24-hour cycle of light and dark, would be utterly shattered, leading to severe psychological and physiological stress. The concept of a day would become meaningless. Time would be measured only by clocks counting down in the darkness. The collapse of the biosphere would be swift and merciless. Photosynthesis would cease instantly, killing all plant life on the surface within days or weeks. The base of the food web would disappear, leading to a mass extinction event that would ripple upwards. Herbivores would starve first, followed quickly by the carnivores that prey on them. Within months, the surface of the Earth would be a silent graveyard, with only the hardiest scavengers and deep-rooted organisms lingering for a short while. The oceans would freeze, but not all at once. The surface would form a thick layer of ice, perhaps several kilometres deep over time. But the immense pressure and residual geothermal heat from the Earth's core could keep a global ocean liquid deep below, just like on the moons of the outer solar system. The atmosphere would undergo a dramatic collapse. The extreme cold would cause the gases to condense and freeze. Carbon dioxide would turn into dry ice snow first, then nitrogen, the main component of our air, would liquefy and freeze, falling as a gentle, lethal rain onto the surface, accumulating in great drifts. Oxygen would follow suit. The atmospheric pressure would drop to a near vacuum, making the surface completely uninhabitable without a pressure suit. The winds would stop, the weather would cease, and an eerie, absolute silence would fall over the globe, broken only by the occasional crack of freezing rock or a tectonic shift. Human civilization as we know it would have almost no chance of survival on the surface. Any hope would lie underground, in bunkers or deep within the Earth's crust, leveraging geothermal energy. These habitats would need to be perfectly self-sufficient, closed ecosystems, generating their own light, air, and food entirely independent of the dead surface. They would rely on nuclear fission or the Earth's internal heat for power. Growing food would require artificial light from massive banks of LEDs, powered by deep geothermal plants or nuclear reactors. The social and psychological challenges of living in such confined, perpetual darkness would be immense. likely leading to new forms of society or a complete breakdown. However, life itself is tenacious. While surface life would be annihilated, ecosystems deep in the ocean, around hydrothermal vents, might survive indefinitely. These communities, based on chemosynthesis, are already independent of sunlight. The slow cooling of the Earth's core would take billions of years, so these deep, dark, hot oases could continue to thrive, completely unaware that the world above has turned into a frozen wasteland. The vent ecosystems, with their tube worms and blind shrimp, would become the primary heirs to the Earth, carrying the torch of biology in the eternal night. For any humans who managed to survive in underground arcologies, their existence would be a desperate struggle. They would become a subterranean species, their world defined by the hum of machinery and the glow of artificial suns. Their knowledge of the surface would become myth and legend. They might even forget that a sky once existed. Exploratory missions to the surface would be extreme undertakings, requiring heated suits and facing a landscape of frozen air and global ice under a black, star-filled sky. The geological record would be preserved with perfect clarity, with no wind, rain, or liquid water to cause erosion. Every mountain range, every canyon, every city would be frozen in time. The ruins of our civilization would stand untouched for eons, a silent monument to a species that once looked up at a blue sky. This mental exercise is more than just a doomsday scenario. It serves to highlight how incredibly fundamental our star is to every aspect of our existence. We take the sun for granted, but it is the engine that drives our climate, our weather, our seasons, and the entire biosphere. Without it, Earth is just another frozen rock adrift in the dark. This perspective also reframes our search for life on other worlds. We often look for Earth-like planets in the habitable zone, but this thought experiment shows that a planet doesn't need to be in that zone to be habitable. It needs internal heat and liquid water. A rogue planet with a hot core can be a life-bearing world, even if its surface is dead. For humanity, the lesson is one of profound fragility. Our technological civilization is a thin veneer on a planet that is, in cosmic terms, perfectly balanced for our existence. The thought of Earth as a rogue planet is a stark reminder of that balance and how quickly it could be lost, forcing us to appreciate the delicate, life-giving connection we have with our star. A connection we are only now beginning to fully understand as we look out at the countless dark wanderers that may share our galaxy. But what if a rogue planet didn't just harbour simple life, but gave rise to an intelligent civilization? The development of a technological species in such an environment would forge a culture and a worldview radically different from our own. Their entire cosmic perspective would be inverted. For them, the default state of a planet is not a sunlit world, but a dark, isolated arc drifting through a void. Their sky would be a permanent, star-studded blackness, with no sun, no moon, and no daybreak. Their astronomy and mythology would be built exclusively upon the fixed background of distant stars and the faint, luminous band of the Milky Way. The concept of a deity associated with a sun would be non-existent. Instead, their planet itself might be venerated as a divine, life-giving entity, a cosmic mother that provides warmth and sustenance from within, independent of any external power. Their understanding of physics would be fundamentally shaped by their environment. They would discover gravity not by watching apples fall, but by studying the motion of objects in their sealed habitats and by deducing the planet's spherical shape from internal seismic studies. Their first great astronomical revelation wouldn't be that worlds orbit stars, but that their own dark world is moving. a realization that might come from meticulously tracking the subtle proper motions of the nearest stars over centuries, the discovery of other star systems, with planets bathed in light, would be a paradigm-shattering event. They might initially view these starlit worlds as hellish, dangerous places, exposed to violent and unpredictable stellar radiation, solar flares, and searing heat. Their own world, stable and protected by miles of rock and ice, might be seen as the safe and natural state of existence. The drive to explore would be immense, but the challenges would be staggering. Their source of energy would not be a distant fusion reactor in the sky, but the planet's own internal heat. Early civilization would likely develop around geothermal vents, harnessing steam and thermal gradients for power. As they advanced, they might master nuclear fission, using isotopes mined from the planet's crust for a truly advanced civilization. Mastering nuclear fusion would be the key to unlocking their world in the space beyond, providing virtually limitless energy to power their habitats and spacecraft. Their technology would be heavily focused on survival in a closed system. They would be masters of recycling, environmental control, and hydroponics long before they ever looked to the stars. Engineering would be directed inwards, towards building and maintaining vast, self-sustaining subterranean cities, with artificial light sources simulating a day-night cycle to maintain biological rhythms. Their medicine would be advanced in treating conditions related to prolonged confinement, low light, and high-pressure environments. When they finally developed spaceflight, it would be a terrifying endeavour, leaving the safety of their underground world for the absolute blackness outside would be a psychological trial unlike any other. Their spacecraft would need to be entirely self-sufficient, carrying their own power and light, as there would be no solar panels to rely on. They might develop a different propulsion technology, perhaps perfected fusion rockets, since chemical rockets would be inefficient for the long journeys between stars. Their targets for exploration would not be other planets in a system, but other rogue planets or, eventually, stellar systems. Finding another rogue planet with a habitable interior would be like discovering an island of potential kinship in a dark ocean. Finding a star system would be like discovering a continent, full of resources but also perceived as full of danger. The very idea of a habitable zone would be foreign to them. Their concept of a good world would be one with a hot, active core and a thick insulating layer of ice or rock. If they were to observe Earth, they might see our world as a bizarre and volatile place, with its thin, unstable atmosphere, its surface scoured by weather and exposed to deadly radiation, and its dependence on a temperamental star. They might even consider it uninhabitable. For us searching for them, the task is equally difficult. We would not look for radio signals or laser pulses, as their civilization might not use such technologies for long-distance communication in the void. Instead, we would look for techno-signatures, unnatural signs. The most promising would be anomalous heat signatures. A rogue planet is supposed to be cold, cooling steadily over billions of years. If we found one that was significantly warmer than models predict, especially with a heat signature that suggests industrial-scale energy use, that would be a powerful indicator. We might look for artificial isotopes in a thin atmosphere, evidence of nuclear activity, or we might look for evidence of massive engineering on a planetary scale, such as structures on the surface that modify its thermal emissions. The existence of such a civilization would force us to confront the sheer diversity of intelligence, their psychology, their art. Their social structures would be moulded by darkness, isolation, and a reliance on internal resources. They might value community and cooperation far more than we do, As individualism in such a fragile environment could be lethal, their history might be one of steady, patient progress, without the cycles of war and expansion that often characterized ours, simply because there was nowhere to expand to until they achieved advanced technology. They are a testament to the adaptability of life and mind, proving that intelligence can flourish in the most unexpected corners of the cosmos, far from the light of any sun. While the idea of intelligent life on distant rogue planets stretches our imagination, we might not need to look that far to find a world with a similar origin story. The evidence for one might be lurking right here in our own solar system, in the form of the hypothetical Planet 9. This isn't about a new planet replacing Pluto, but a genuine, yet to be seen giant, thought to be orbiting far beyond Neptune in a vast, elongated path. The case for Planet 9 isn't based on direct observation, but on the peculiar behaviour of a group of small, icy bodies in the Kuiper Belt, the ring of debris left over from the solar system's formation. Astronomers notice that the orbits of these distant objects are clustered in a way that defies random chance. Their points of closest approach to the Sun are grouped together, and their orbits are tilted in a similar direction. This gravitational alignment is a strong hint that a massive object, with a weight several times that of Earth, is shepherding them, its gravity orchestrating their paths from the dark outer reaches. The proposed orbit for this world is incredibly wide and eccentric, taking it from a few hundred astronomical units from the Sun at its closest to well over 1,000 at its farthest, meaning one full orbit could take 10,000 years or more. This strange, detached path is a key piece of evidence suggesting that Planet 9 may not have formed in its current location. The classical model of planetary formation involves dust and gas coalescing in a relatively calm disk around a young star. But an orbit so far out and so tilted doesn't fit that picture easily. Instead, the leading theory is that Planet 9 is a captured rogue planet, an interstellar wanderer that was snared by the Sun's gravity during the solar system's chaotic early days. Imagine the young Sun surrounded by its protoplanetary disk, with countless planetary embryos jostling for position. In this crowded environment, the gravitational pull of giant planets like Jupiter and Saturn could have flung some objects out into the void, but the same dynamics could also have captured a planet that was passing by. A free-floating planet, drifting through the nascent solar system, could have been slowed down just enough by gravitational interactions with the gas disk or other bodies to be trapped in a stable, albeit distant, orbit. This capture scenario explains the odd orbital parameters perfectly. A captured object would likely end up in a highly inclined and elliptical orbit, unlike the relatively flat and circular orbits of planets that formed in place. The existence of such a world would rewrite the early history of our solar system, revealing a past filled with more gravitational violence and interstellar exchange than we previously thought. It would mean that our cosmic neighbourhood is not entirely composed of native-born worlds, but might include an adopted immigrant from the vast galactic population of rogue planets. The hunt for Planet 9 is now a major endeavour in astronomy, combining sophisticated computer modelling with painstaking observational campaigns. Researchers use the observed orbits of the Kuiper Belt objects to narrow down the possible location of the unseen planet, creating a celestial treasure map. Then, powerful telescopes like Subaru in Hawaii and the Vera C, Rubin Observatory in Chile scan these predicted swaths of sky, looking for a faint point of light moving slowly against the backdrop of fixed stars. The challenge is immense. The planet is incredibly far away, receiving very little sunlight, and reflecting even less back to us, making it extraordinarily dim. It's like looking for a single charcoal briquette in the vastness of a dark forest at night, despite the difficulties. The potential reward is huge. Finding Planet 9 would be a monumental discovery, not just for adding a new planet to our system, but for the opportunity to study a captured rogue planet up close. We could analyse its atmosphere, composition, and size, providing a direct sample of an object that formed independently of a star or was ejected from another system. This data would be invaluable for testing our models of both planetary formation and the dynamics of interstellar capture. It would validate the idea that rogue planets can be snagged by stars, implying that many other stellar systems might host similar captured worlds, expanding the diversity of planetary systems in the galaxy. The implications for the abundance of life are also intriguing. If Planet 9 has a thick atmosphere that traps internal heat, or if it has a large moon heated by tidal forces, it could, in theory, host a subsurface ocean. While this is a long shot given its likely frigid state, it reminds us that habitable conditions can exist in surprising places. The search itself is driving technological innovation, pushing the limits of telescope sensitivity and data analysis techniques. Even if Planet 9 is never found, the pursuit has already deepened our understanding of the solar system's outer limits and the gravitational forces that shape it. The hypothesis has also sparked related ideas, such as the possibility of other captured objects or even a primordial black hole, though a planet remains the most favoured explanation for the public. The story of Planet 9 captures the imagination, a reminder that our solar system still holds major secrets and that exploration is an ongoing process. It bridges the gap between the familiar planets and the exotic rogue worlds we've been discussing, showing that the boundary between our system and the interstellar medium is porous. The potential discovery would be a beautiful confluence of theory and observation, a testament to human curiosity and our relentless drive to map our cosmic home. So, while we gaze at the stars wondering about distant rogue planets, we should also remember to look closer to home, where a giant might be hiding in the shadows, waiting to tell its story of exile and capture, a story that connects our humble solar system to the grand, dynamic ballet of the galaxy. This ongoing mystery exemplifies how science works, with clues from small objects pointing to a larger truth, and how every answer uncovers new questions, keeping the adventure of discovery forever alive. The stark environment of a rogue planet creates a geological reality unlike anything on Earth, a world where the surface exists in a state of near-perfect preservation, a sleeping landscape where change is measured in billions of years, without a star. The powerful external forces that constantly reshape terrestrial planets are almost entirely absent. There is no liquid water to carve canyons, no rainfall to weather mountains, no wind to scour plains, and no freeze-thaw cycles to crack rock. The concept of erosion as we know it practically ceases to exist. The landscape you see today would be virtually identical to the landscape a billion years ago, making the surface a breathtakingly ancient and static museum of the planet's most violent and formative events. The primary shapers of the terrain would be internal forces and occasional external bombardments. Tectonic activity, driven by the planet's internal heat, could still push up mountain ranges or create vast rift valleys, but these features would remain sharp and jagged, their edges never softened by weather. Cryovolcanoes, erupting slushy mixtures of water, ammonia, DOT, and methane could build up strange, frozen constructs that would stand unchanged for eons, their bizarre shapes silently testifying to the planet's inner warmth. But the most dominant feature on the surface would undoubtedly be impact craters. On Earth, the Moon, or Mars, DOT. We see cratered landscapes, but even those are modified over time. On the Moon, Subsequent impacts and the slow process of space weathering gradually alter the craters. On Earth, they are erased with geological speed. On a rogue planet, however, every single impact, from the smallest micrometeorite to the largest asteroid, would leave a permanent scar. The surface would become a cumulative record of bombardment, a pockmarked testament to its journey through the galaxy. You would see craters superimposed on top of older craters, creating a palimpsest of cosmic violence. The number of craters would be far greater than on any body in our solar system, because there would be no geological resurfacing to erase them. This provides an incredible opportunity for scientific study. By analysing the density and distribution of craters, planetary scientists could determine the relative ages of different surface regions and piece together a history of the impact to population in the interstellar medium. It would be like having a fossil record of the galaxy's minor bodies, preserved in ice and rock. The composition of the surface would also be unique. With the atmosphere largely frozen out, the ground would be covered in layers of ices, not just water ice, but nitrogen ice, carbon dioxide ice, and others, forming a complex, stratified crust. These ices would not flow like glaciers on Earth. They would be brittle and rigid at such low temperatures. The surface might feature vast, smooth plains of frozen nitrogen, punctuated by rugged highlands of water ice and rock. The colours would be muted, primarily whites and greys, with potential subtle hues from complex organic molecules or irradiated ices. Without weathering, the surface materials would remain chemically pristine, offering a direct sample of the planet's original composition and any materials delivered by comets and asteroids. This slow-motion geology has implications for any potential future exploration. A rover on such a world would not have to contend with sandstorms or dust devils. Its tracks would remain visible for millions of years. The main challenges would be the extreme cold, the potential instability of the ices, and the need to navigate a treacherous, cratered terrain. A lander would find a surface that is both incredibly old and incredibly fragile, a window back in time to the early solar system, but preserved in the deep freeze of interstellar space. This static nature contrasts sharply with the potentially dynamic interior. While the surface sleeps, the inside of the planet could still be active, with a hot core, a molten mantle, and perhaps a global subsurface ocean. This creates a world of two halves, a dead, frozen crust and a living, warm heart. The interaction between them would be minimal, limited to occasional cryovolcanic eruptions that might patch small areas with fresh ice, only for that new ice to then remain untouched forever. This profound lack of erosion is a key characteristic that distinguishes rogue planets from their stellar-bound cousins. It means that these worlds are not just drifting through space, they are preserving it, holding a record of cosmic history that is elsewhere lost to time. They are the ultimate archives. Their surface is a history book written in craters and untouched geology, waiting for a reader who can understand its language. In a universe of constant change, these worlds offer a rare glimpse of permanence, a frozen moment in the life of a planet that has escaped the relentless ticking of the geological clock driven by a star. Reaching one of these frozen, ancient worlds represents the absolute pinnacle of human exploration, a challenge that dwarfs any voyage ever attempted and pushes the limits of our technology, courage, and very conception of what it means to be a spacefaring species. The first and most formidable obstacle is simply getting there. A rogue planet does not orbit a convenient, bright star that we can aim for. It is a dark, moving target in the immense void between stellar systems, Travelling to even the nearest suspected rogue planet would require a journey lasting centuries, if not millennia. This rules out any conventional chemical propulsion. We would need revolutionary propulsion systems, such as continuous fusion rockets, immense light sails powered by giant lasers, or even more speculative technologies like matter-antimatter annihilation. The spacecraft itself would need to be a veritable world ship, a self-sustaining ark capable of supporting multiple generations of crew in a perfectly closed ecological system. Every gram of water, oxygen, and nutrient would have to be recycled with near total efficiency. A biological and engineering challenge we are only beginning to understand. The ship would need to be largely self-repairing, carrying advanced manufacturing capabilities like 3D printers and stocks of raw materials to fix any system that fails over the centuries. The social structure aboard such a vessel would have to be meticulously planned to maintain knowledge, purpose, and mental stability across generations born into the journey, who may never see their destination or Earth itself. Navigation would be another immense hurdle. Without the gravitational anchor of a star system, the spacecraft would be navigating by dead reckoning through a featureless sea of black, constantly correcting its course using the faint positions of pulsars or other galactic landmarks. Once the planet is reached, the mission would enter its most dangerous phase, approaching a dark dot, non-reflective object with no surrounding system of orbiting moons to provide clues about its gravity. Would be a navigational nightmare. The landing would be conducted in near total darkness, illuminated only by the ship's own powerful lights, on a surface that could be treacherous with unstable ices and deep craters. So why would we ever attempt such a monumental task? The motivations are as powerful as the challenges are daunting. The primary driver would be pure, unadulterated science. A rogue planet is a pristine time capsule, its surface unweathered for billions of years, offering a direct look at the building blocks of planetary systems and the history of galactic bombardment. It could hold answers to fundamental questions about how planets form and evolve. The search for life is an even more compelling reason. Landing on a rogue planet with a subsurface ocean, drilling through the ice, and sending a probe into the dark waters below could lead to the most profound discovery in human history: alien life, finding a second. Independent genesis of life would tell us that biology is a universal imperative, not a fluke confined to Earth. The potential resources, while not a primary motivator given the astronomical cost, cannot be ignored. A rogue planet could be a rich source of water ice, which could be split into hydrogen and oxygen for rocket fuel, making it a potential stepping stone and refueling depot for further interstellar travel. Its core might contain rare metals and minerals, though mining them in such an environment would be an engineering feat of epic proportions. There is also a powerful, long-term survival motive. Establishing a colony on a rogue planet would create a human outpost that is completely independent of any star. This offers a unique form of security. While stars can die, become unstable, or have their planetary systems disrupted, a rogue planet colony, powered by its own internal geothermal or nuclear energy, could potentially survive for billions of years, safe from stellar cataclysms. It would be the ultimate insurance policy for humanity. However, the reality of life on such a world would be one of extreme confinement and psychological strain. The colonists would live almost entirely underground, in habitats carved into the ice or rock, huddled around the warmth of nuclear reactors or geothermal taps. The surface would be a lethal, airless wasteland to be visited only in heavily armoured suits for brief periods of research or resource gathering. The sky would be a permanent black, the sun a distant, irrelevant speck. the sense of isolation would be profound, knowing that the nearest human civilization is light years away, and that communication with Earth would involve time lags of decades or centuries. This existence would fundamentally change what it means to be human, creating a culture of deep-seated resilience and a worldview centered on internal resources and community cohesion, completely divorced from the natural rhythms of a sunlit world. The children born there would know of Earth only as a legend, a mythical blue and green world they have never seen. The technological spin-offs from such an endeavor would be immense, revolutionizing energy production, recycling, closed-loop life support, and long-duration spaceflight, benefits that would ripple through society on Earth. The mission to a rogue planet is not something for the near future. It is a goal for a mature, interstellar-capable civilization. It represents a test of our species' endurance, ingenuity, and will to explore. It is the journey from being a species of a single world to becoming a truly interstellar one, capable of making a home even in the coldest, darkest, and most lonely places the galaxy has to offer. The very act of attempting it would redefine our potential and mark our coming of age in the cosmic community. These drifting worlds could be more than just potential homes for life. They might be the galaxy's ultimate sailors, silent vessels responsible for spreading the seeds of life between the stars. This idea, known as panspermia, suggests that life is not something that uniquely originates on each habitable world, but can be transported across space, and rogue planets are perfectly designed for this role. Imagine a rogue planet with a subsurface ocean teeming with microbial life. This ocean is a stable, protected environment, shielded from radiation and temperature extremes by kilometers of ice. Now, imagine a massive impact on the surface. A large asteroid or comet slams into the icy crust. The force of the impact is tremendous, and it can eject plumes of material from the ocean out into space. Within this ejected material could be droplets of water containing hardy, dormant microbes, similar to extremophiles on Earth that can survive in space for extended periods. These tiny, frozen droplets, encasing life, now become independent travellers. They are propelled away from the rogue planet, but because the planet itself is moving, these life-bearing rocks are given a starting velocity that carries them on their own trajectories through the galaxy. The journey is long, millions or even billions of years, but space is cold and quiet, acting as a natural deep freeze that preserves the dormant organisms. These microscopic astronauts are protected within their rocky spacecraft, shielded from the worst of cosmic radiation. Eventually, by pure chance, one of these rocks might encounter another planetary system. It could be captured by the gravity of a star or a giant planet and drawn inward. As it enters the new system, it might collide with a young, habitable world, or be gently captured into its orbit. Upon entering the atmosphere of a planet with liquid water on its surface, the rock heats up, but the interior can remain cool, protecting its microbial passengers. It crashes into a warm ocean, the ice melts, and the dormant microbes are released into a new, fertile environment. If the conditions are right, they can awaken, reproduce, and begin the process of colonizing this new world. This entire process turns the concept of life's origin on its head. Instead of life arising independently on Earth around hydrothermal vents, it could have been delivered here by a rogue planet that passed near our solar system billions of years ago. This would mean that all life in the galaxy could be related, sharing a common ancestor that evolved on one single world long ago and was then scattered across the stars by these dark arcs. Rogue planets are ideal for this purpose for several reasons. Their journeys are immensely long. giving them ample time to cross between stellar systems. Their subsurface oceans provide a stable, long-term habitat for life to thrive and evolve before being ejected, unlike comets, which have orbits that regularly bring them close to stars where radiation can sterilize them. A rogue planet's dark journey keeps its biological cargo in a pristine, frozen state. The probability of a successful transfer might be low, but given the potential billions of rogue planets in the galaxy, each with billions of years to travel, the numbers start to work in favour of panspermia happening frequently. This theory transforms the galaxy from a collection of isolated islands of life into a single, interconnected biosphere. Life is not something that happens on a planet. It is something that happens to a planet. An infection that spreads from world to world. Rogue planets are the vectors of this infection. The silent, slow-moving ships in a grand, biological diaspora. This also solves the problem of the apparent speed with which life arose on Earth, soon after the planet cooled and oceans formed. Evidence suggests life was already present. If life had to start from scratch through random chemical reactions, this seems remarkably fast. But if life was delivered ready-made, it explains the quick start. The implications for the search for life are profound. If panspermia is true, then we might expect to find life with a similar biochemical basis elsewhere. The DNA and protein structures of alien life might be recognizably similar to our own, because we share a common cosmic ancestor. When we explore the oceans of Europa or Enceladus, we might not find truly alien life, but rather distant cousins. This idea also gives rogue planets a cosmic purpose. They are not failed worlds or lonely exiles. They are the gardeners of the galaxy, ensuring that life, once it arises, does not remain in one place but gets a chance to spread and adapt to new environments. They are the great connectors in an otherwise disconnected universe for humanity. This offers a new origin story, one that ties us not just to Earth, but to a lineage that spans the Milky Way. Our family tree may have roots on a world we cannot even imagine, a world that cast its biological message in a bottle into the cosmic ocean, and Earth was the shore it washed up on. This transforms our perspective on these dark wanderers from objects of curiosity to potential relatives, the ancient progenitors that may have carried the spark that eventually led to us. The study of rogue planets, therefore, is not just about planetary science. It is about tracing our own deepest ancestry and understanding the mechanisms that make the universe a living, connected whole. The discovery of these solitary wanderers has thrown a wrench into what we thought was a settled scientific question, forcing astronomers to grapple with a fundamental dilemma. What, exactly, is a planet? For a long time, we had a working definition, but the official one came from the International Astronomical Union in 2006, primarily to address the Pluto situation. Their definition states that a planet must orbit the Sun, must be massive enough to be rounded by its own gravity, and must have cleared its orbital neighbourhood of other debris. This definition works neatly for our solar system, but it immediately creates a problem for rogue planets. By the strict letter of the law, they are not planets at all, because the first criterion requires them to orbit our Sun, which they clearly do not. A more general interpretation says a star dot. But the point remains, a free-floating object fails this basic test. This has created a taxonomic crisis, a cosmic identity crisis for countless worlds. Are they not planets simply because they lack a stellar parent? This seems like a terribly geocentric, or rather, heliocentric, view to take. It prioritizes where an object is over what an object is. This has sparked a vigorous debate within the scientific community about whether we should classify objects based on their intrinsic physical properties or their dynamical history. The intrinsic property argument says that what matters is the object itself, its mass, its shape, its geology. If it's a sphere of rock or gas, below the limit for deuterium fusion that defines a brown dwarf, then it should be a planet, regardless of whether it orbits a star, a brown dwarf, or nothing at all. This is a clean, physics-based definition. The formation history argument is more nuanced. It suggests that a true planet must have formed within a circumstellar disk, the swirling cloud of material around a young star. This would include ejected worlds, but exclude the orphans of the cloud. Those objects that formed directly from the collapse of a gas cloud, like a star but on a smaller scale. The problem is that from a distance, and with our current technology, it is often impossible to tell how a specific rogue planet formed. We can estimate its mass and temperature, but its birth certificate is lost to time. This isn't just semantic quibbling. It has real consequences for how we search for, catalogue, dot, and study these objects. If they are not planets, what are they? Some proposed names include sub-brown dwarfs, dot for planemos for planetary mass objects, or simply free-floating planets. But this proliferation of terms can create confusion. The debate touches on deeper philosophical issues about how we categorize the natural world. Our definitions are often born from our own limited experience. We defined planets based on the 8 that orbit our sun, and then we discovered a whole new class of objects that challenge that parochial view. It is a reminder that nature does not care for our neat little boxes. It produces a continuum of objects, and our job is to create a classification system that reflects reality, not one that forces reality to conform to our preconceptions. The resolution of this debate will shape textbooks, research grants, and public understanding for decades to come. If the definition is changed to be based on intrinsic properties, the number of planets in our galaxy would instantly skyrocket into the billions. If the current definition stands, we are essentially saying that the most common type of planetary mass object in the galaxy does not qualify as a planet, which seems a rather absurd conclusion. This also impacts the study of exoplanets. If a rogue planet is not a planet, then what is an exoplanet that has been ejected from its system? It was a planet, and now it is not. This seems messy. The discussion forces us to think about what the essence of planethood really is. Is it about being a primary world, a dominant gravitational body in its local space? A rogue planet is certainly that, even if its local space is empty. Is it about the potential for geology and atmosphere? Many rogue planets have both. Is it about the potential for life? As we have discussed, that potential certainly exists. By grappling with these questions, we are doing more than just arguing about words. We are refining our understanding of our place in the cosmos. We are moving from a solar system-centric view to a truly galactic perspective. The universe is far more diverse and weird than we imagined, and our language and categories need to evolve to keep up. The humble rogue planet, silent and dark, has become the catalyst for a profound scientific and philosophical evolution, pushing us to create a more inclusive and accurate map of the cosmic zoo. This process is a hallmark of good science. When new data contradicts old models, we don't ignore the data, we change the models. The rogue planet definition debate is a living, breathing example of the scientific method in action, showing that our knowledge is never complete and that the most exciting discoveries are often the ones that force us to rethink what we thought we knew. The sensory experience on a rogue planet would be as alien as its environment, and perhaps the most profound departure from Earth would be the nature of sound, or more accurately, dot, the crushing, absolute lack of it. The behaviour of sound is entirely dependent on the state of the atmosphere, and on a world where the air has frozen and collapsed, the result is a silence so complete it becomes a physical presence. Imagine standing on the surface of such a world. You would be surrounded by a landscape of frozen gases and ice, under a black sky filled with unmoving stars. You shout, but no sound comes out. You clap your hands together, and you see the motion. You feel the impact in your gloves, but you hear nothing. There is no medium for the sound waves to travel through. The air pressure is effectively zero, a vacuum as good as that of open space. This isn't the quiet of a remote forest. It is the total, absolute negation of sound. The only vibrations would be those transmitted through the solid ground itself, a faint tremor from a distant meteor impact, a deep rumble from a tectonic shift far below. You would feel these through your boots, a subtle vibration in your bones, but your ears would register nothing. This acoustic emptiness would be psychologically unnerving, amplifying the visual isolation and creating a sense of profound sensory deprivation. The world is not just dead, it is mute. Now, contrast this with a rogue planet that has managed to retain a thick atmosphere, perhaps one dominated by hydrogen. Here, sound would behave, but in strange and unfamiliar ways. Sound travels faster and behaves differently in various gas mixtures. In a dense hydrogen atmosphere, the speed of sound would be much faster than in Earth's nitrogen-oxygen air. A sound generated a kilometre away would reach you significantly quicker, creating a disorienting effect where the world feels acoustically smaller. The tones and pitches of sounds would be distorted, shifted, making even a human voice sound alien and deep. However, the sources of natural sound would be exceedingly rare. There would be no bird song, no rustling leaves, no flowing water. The soundscape would be dominated by the occasional geological event. You might hear the deep, thunderous roar of a cryovolcanic eruption, the sound waves propagating through the thick, cold air. You could hear the crack and groan of the ice crust as it shifts under tidal stress or internal pressure, a sound like a giant glacier carving but spread across a continent. If there were winds, they would sound different, deeper, slower, and more resonant as they swept across frozen plains and through canyons of ice. For any potential life in a subsurface ocean, the acoustic environment would be entirely different yet again. Sound travels exceptionally well in water, faster and farther than in air. In the perpetual darkness of a buried sea, sound could be the primary sense, the way sight is for us on Earth. Life forms might use sonar for navigation and hunting, filling the water with clicks and whistles. They might communicate with complex songs that carry for hundreds of miles in the liquid medium. The constant background noise could be the low-frequency rumble of hydrothermal vents and the shifting of the ice ceiling above. For them, their world is not silent at all. It is a rich, vibrant tapestry of sound, a stark contrast to the dead quiet of the surface. This dichotomy between the soundless surface and the potentially noisy interior highlights the layered nature of these worlds. An explorer on the surface would experience a realm of terrifying quiet, where every small movement inside their suit would be magnified by the lack of external noise. The whir of a camera motor, the hiss of their own breath, the beat of their own heart would become the dominant sounds in their universe, a constant reminder of their own fragility in the immense, silent void, ... This acoustic signature is also a potential tool for detection and study. While we cannot listen directly from light years away, the presence or absence of an atmosphere, which dictates the soundscape, can be inferred through other means. A world with a substantial atmosphere will have a different thermal profile and might show signs of atmospheric circulation in its infrared emissions. A world with a collapsed atmosphere will be uniformly cold and much harder to detect. In the end, the soundscape of a rogue planet forces us to think about perception itself. Our human experience is built around a certain set of environmental conditions, including a particular atmosphere that transmits sound in a specific way. Alter those conditions, and the very fabric of experience changes. The eternal silence of a frozen surface is as much a defining characteristic of these worlds as their cold and dark, a final, stark symbol of their separation from the warm, noisy, vibrant world we call home. It is a reminder that the universe is not only visually diverse, but acoustically diverse as well. And that much of it is, from our perspective, utterly and profoundly silent. The cumulative effect of everything we have learned about these rogue planets forces a profound and humbling shift in our cosmic perspective, fundamentally redefining what we thought we knew about worlds and our place among them. For centuries, our understanding was built on a simple, seemingly self-evident premise. Planets are satellites of stars. Our entire astronomical vocabulary, our search for life, our imagination of other worlds, all of it was rooted in the model of our own solar system. We assumed that life, if it existed elsewhere, would need the light and warmth of a sun, confining our concept of habitable real estate to a thin, golden shell around each star. The discovery that planets can not only exist but potentially thrive in the absolute cold and dark of interstellar space shatters that paradigm. It forces us to realise that our Earth is not the standard model for a planet. It is a specific variant, a sunlit, warm, and stormy world in a universe that may be dominated by dark, cold, and silent ones. This is a Copernican revolution for the planetary age. We are not living on a typical world in a typical system. We are living in a special, perhaps even rare, kind of environment. The galaxy, it turns out, is not just a collection of stellar systems with planets orbiting them. It is a fluid, dynamic sea of matter where worlds are as common in the voids as they are around the lights. This realization expands the canvas of potential life exponentially. The habitable zone is no longer a narrow band around a star. It is any volume of space containing a world with sufficient internal heat and liquid water. This means the number of potential habitats for life could be orders of magnitude larger than we ever dreamed. Life is not a delicate flame that can only flicker near a stellar furnace. It is a tenacious spark that can glow using its own internal fire, hidden away in the deepest, darkest places. This new perspective is both exhilarating and sobering. It is exhilarating because it suggests that life could be incredibly common, though almost entirely hidden from our view, thriving in subsurface oceans across the galaxy. It is sobering because it highlights our own isolation. We are creatures of the light, adapted to a very specific and, it seems, uncommon set of conditions. Our civilization, built on the surface of a world bathed in energy from a star, might be the exception, not the rule. The silent, dark majority of worlds are utterly alien to our experience. This knowledge should instill a deep sense of cosmic humility. We are not the centre of the universe, nor are we the model for what a world should be. We are one possibility among a staggering array of others. This understanding also redefines the future of exploration. Our ultimate journey may not be to other Earth-like planets orbiting other suns, but to these dark wanderers, to drill through their ice and explore their hidden seas. They represent the final frontier, not because they are far away in distance, but because they challenge everything we thought we knew about what a world is. The study of rogue planets teaches us about resilience and adaptation. It shows that planetary bodies are not passive rocks, but dynamic entities with internal engines that can sustain environments for billions of years without any external input. It reveals that the processes of planet formation are more violent and chaotic than we knew, capable of flinging worlds into the void by the billions. In the grand tapestry of the cosmos, we are now learning to see the dark threads, the ones we never noticed before, but which may form the majority of the fabric. Our galaxy is not just a spattering of lights with a few dots around them. It is a vast, three-dimensional network of worlds, most of them dark, cold, and solitary, each on its own epic journey. This expanded view does not diminish our world. It enhances our appreciation for its specific, beautiful, and life-giving conditions. The blue sky, the warm sun, the changing seasons. These are not universal constants. They are the precious, local conditions of our home, a vibrant oasis in a silent, dark ocean. As we look up at the night sky, we can now imagine not just the points of light, but the countless dark companions drifting among them, a hidden population that completes our picture of the galaxy. This is the ultimate lesson of the rogue planets. The universe is far stranger, more diverse, and more wonderful than we ever dared to imagine, and our journey to understand it has only just begun.